This video is part of the Commercial Building Electrical Design series. We're talking about power distribution design. We want to continue our discussions about basic materials, and in this video we're going to look at the tap rule and some other methods beyond what we've already discussed. So in the progression of things under the power distribution design, we have covered delivery systems. We're still talking about materials, and as I said before, we're looking at tap rule and other methods. So while in most applications in commercial building electrical design we utilize pipe and wire to run circuits, there are other methods available to accomplish this. So in this section we'll explore some of those more common alternate methods used in industry today and some of the important aspects of their typical applications. So we want to talk about the tap rule. The tap rule is an important concept or method allowed by the National Electrical Code that can be very useful but is also many times misunderstood by designers. In general, the National Electrical Code requires that all conductors are to be protected by some type of overcurrent protection that is equal to or less than the ampere rating of the conductors for its specific use or application or installation. So this can be accomplished by using circuit breakers, fuses, protective relays, etc. But the idea is that if the amps seen by the conductor exceed the rating of the conductor for some excessive amount of time, the circuit must be interrupted to prevent the conductor, or more importantly the conductor's insulation, from experiencing any damage which might cause the conductor to become exposed, which would be very hazardous. This can easily be accomplished by using a panel with circuit breakers, as will be shown later, or using a fuse disconnect, but it can be costly or difficult to place a panel anytime you have more than one load that needs to be fed. For example, a common occurrence of this is the case of multiple condensing units placed outside of a building. They can usually range in number from 1 to 6 or more and must all be fed separately. In most cases, it is not cost-effective to place a panel in this location, and it may be that the units are located at a significant distance from the nearest panel. In this case, the tap rule can be utilized to remedy this situation. The way this is done is that a feeder, which we'll talk about later, is run to the location of the loads that can accommodate the combination of the loads. From this feeder, the branch circuits feeding each of the loads is tapped off of the feeder, and separate conductors are then used to feed each load using a tap connector as shown here. So this is usually done in a wireway. We'll talk about that later, but this is a typical tap connection that you might see inside of a wireway. And the point here is when we do the tap, we usually use conductors that are smaller than the feeder conductors. And so this is an important aspect of this. The branch conductor sizes required to feed these loads is typically much smaller than the feeder size and therefore are not adequately protected by the feeder breaker, as it is usually much larger in size than the rating of the branch circuit conductors. This being the case, as it stands as described, these branch conductors are now not adequately protected, which in general is a code violation. This is where NEC Article 240.21 is utilized, as it says that for these tapped conductors, they may in general be allowed to run up to 10 feet from the tap and then be protected by some type of overcurrent device. Again, this could be a fuse disconnect, enclosed circuit breaker, etc. So it also gives special conditions where this distance can be extended, but for most loads, 10 feet is usually adequate. And as we shall see in the next section, there are methods that can be utilized to simplify this process. So let's talk about wireways. So wireways, also referred to as wire troughs, are nothing more than enclosures that are used to house conductors. The use of metallic wireways is governed by NEC Article 376. When they are used in conjunction with a piece of gear, as in extending the area for running conductors for a panel or switchboard, then they are referred to as an auxiliary gutter. The use of auxiliary gutters is a little bit different, and it's governed by Article 366. So we can see in this picture here, this is where the wireway is being used as an auxiliary gutter to extend the space of the panels. The primary function of a metallic wireway in general is to facilitate the implementation of the tap rule. The tap rule is defined in the NEC in Article 240.21 and is discussed in detail in the previous section. To utilize or facilitate the tap rule, wireways are specified such that they are long enough to accommodate the number of taps and their associated overcurrent protection devices necessary to supply the number and size of the localized loads and large enough in cross-section to accommodate the number and size of conductors to supply the tap loads. So this is a detail that I've used on some of my drawings. It shows a common elevation for a wire trough utilized for taps, and then you see that while we have plenty of space here, we might not need as much space for the taps, we might need it to accommodate the disconnect spacing. So this is a 4x4 by 10 foot trough. It's NEMA 3R, and because it's used outdoors. So we have our incoming feeder here, which it runs the length, and then we have those tap connections that we tap off, go through these disconnects and feed the associated loads. So here's a picture of wireway in actual service here. So this is they're utilizing the tap rule for multiple meters and services. So this would be like for a strip mall, so you'd have separate stores. So each store you'd want to have their own separate meter because they all want to pay their own separate electric bill. And so the main service comes in with these two conductors, these two conduits into the wire trough and runs the length of the wire trough, and then we tap off those conductors, go through the meter, then go through the disconnect. So this is your main disconnect, and so this is your 10-foot span. We're within 10 feet, so we have a fused disconnect, and then they go underground to feed the separate store locations. So cable tray is an assembly of a solid or ladder type tray system or structure that is used to distribute conductors throughout a facility or space. And here's a picture of what they might look like over here. You can see you can have solid bottom, you can have perforated bottom, or you can have ladder type. So the use of cable tray is governed by NEC Article 392. Cable trays are not typically used in commercial building construction to distribute power circuits, but rather they are more commonly used to distribute telecommunications circuits. They are frequently used to distribute power and telecommunication circuits in industrial applications. Cable tray is ideal for telecommunication distribution in commercial building as it offers the most flexibility for future growth and technology upgrades. So as we all know, technology keeps advancing and improving at a really fast pace, so you want to have the flexibility to be able to change that out as it changes. Cable tray can be constructed of either steel or aluminum and can be in many different forms, including solid all the way to different ladder patterns. Busway or bus duct is an assembly consisting of a grounded metal enclosure that houses exposed or insulated copper or aluminum conductors, usually in the form of bus bars. The use of busway is governed by NEC Article 368. There are basically two types of busway, which are feeder bus and plug-in busway. Feeder bus type busway is a low impedance bus connection between large pieces of gear or equipment. It is intended to be used in lieu of pipe and wire to run a feeder circuit. In this type of busway, the buses are typically insulated and grouped tightly together to make the busway compact as shown here. So in this picture here, you can see the busways right here compactly together as they're insulated. Because of the compact grouping of the buses, there's really no opportunity to tap this type of busway. So their only connection is at the source and at the load where the busway is terminated. So again, this is designed to take the place of feeder conductors and feeder conduits. So if you had a large panel like up on the top floor of a high-rise, say like 1200 amps, you might have to run 4 large conduits up there to feed that panel. Well, one option would be you could just use low impedance bus duct to feed that panel up there, which uses much less space. So this is in contrast to plug-in type busway, which is typically used to supply multiple loads as it runs throughout a facility. This is done by using a bus plug device, which basically taps the bus assembly utilizing the tap rule and providing overcurrent switching device to then be used to supply an electrical load. Unlike the feeder type busway, the buses are equally spaced as shown above for the entire run to allow room to insert a tap box or plug-in unit as shown below. Either of these types of busway assemblies can be found in commercial building construction, especially in larger projects or multi-story or high-rise projects. But they're probably most commonly utilized in industrial applications, like if you have an assembly line and you might move equipment around. So you can see the buses aren't spaced quite as close together. You have these like penetration areas where you can insert a plug-in unit, and so this is what it looks like when the unit is plugged in, and this is where you could plug in a separate one here.